Alright, so next we'll look at the Borel measure. Now the Borel measure is specifically defined on a locally compact Hausdorff space, so we need to know what that means. Let X, together with some topology, be a topological space. A collection, script A, of subsets of X is said to cover the space X, or it's said to be an open covering, or be a covering of the space X if the space X is the union of the subsets. And this collection, script A, is an open covering of the space if each of the subsets, a sub I, is in the topology for every index I. And a subset of the collection A that also covers the space X is called a subcover. Alright, so notice that for any topological space, the basis itself can be a covering, or is a covering of the space, because it does indeed span the space. And if there is and that basis is an open covering, and if there is a subset of that, or of any given cover, then we call that subset that also covers the space X, we call that subset a subcover. Right? A topological space X is called, or is, compact if every open cover of the space has a finite subcover. And a space X is locally compact if every point has a neighborhood whose closure is compact. Alright, so now we can define a Borel measure. Let X be a locally compact Hausdorff space. And let script B be the Borel sigma algebra in the space X. Then the function mu mapping the sigma algebra into the non-negative subset of the extended real line is a Borel measure on the space X. Well, specifically on the sigma algebra, but we often just say on the space. All right. Now, whereas the Borel measure is defined on a locally compact Hausdorff space, the Lebesque measure is defined on a finite dimensional real space, or a space that is homeomorphic to a finite dimensional real space. Now, the definition we're going to give is not the most abstract and not the most general, but given the measure theory that we've covered so far, this is probably the most general definition that we can give. So let script B be the Borel sigma algebra. Or in finite dimensional real space. And let the function lambda from the Borel sigma algebra into the non-negative subset of the extended real line be defined by lambda of a set A, a measurable set A, is the product of interval length b sub I minus b sub A if the set A is a product of intervals and 0 if the set A is a finite point set, or the empty set. Then the extension, or the completion, of the function lambda is a Lebesque measure on the finite dimensional real space. All right, so we'll look at an example on the real line. So in the real line, we're going to look at the Lebesque measure of a closed interval from A to B. This is the measure of a union consisting of the singleton set A with the open interval from A to B, and with the singleton set containing the point B. So this is a sum. These are mutually disjoint, so this is the sum of the measures. Now, every finite point set has measure 0, and so this is the same as the measure of the open interval from A to B, which is the interval length. So a Lebesque measure is a generalization of length of intervals. So in higher dimensional real space, for instance, in two-dimensional real space, we're looking at an area. So in one dimension, it's a single length. In 2 dimensions, we're looking at an area. In 3 dimensions, we're looking at a volume. And in higher dimensions, we're looking at the higher dimensional analogs of volume. All right? So we'll end the lecture here. Next time, we'll look at the metric topology and metric spaces. So I hope you have enjoyed the 16th lecture. Thanks for watching.